Hello everyone, I'm Goksel and this is my Cmpe 492 project called Verification of Multithreaded Software using Bounded Model Checking and Llvm framework. This project focuses on concurrency bugs of the programs. Multithreaded programs may contain bugs which are specific to them, such as deadlocks, race conditions, or mutual exclusions. One of the main reasons is the exponential number of behaviors because of non-predetermined thread schedulings. Visual testing is not enough to find bugs in concurrent programs, while formal verification gives 100% coverage. As some background, bounded model checking is searching for a counterexample in a SAT or SMT formula to make it satisfiable for a given finite execution length. That formula can be solved using efficient solvers such as MATSAT. Llvm is an instruction and type system which supports various languages. This is a nice advantage because after the tool is completed, programs with different languages can be converted to a common Llvm code. Computational software verification, or shortly SVComp, is our main focus for this semester. It's a competition for verification tools all around the world. Its main purposes are establishing a set of benchmarks for software verification and providing a snapshot of the state of art in software verification to the community. For more details, you can visit the following address. Our methodology is first converting the code to be verified to Llvm IR representation using Clang and Llvm. Then, the .ll file created by the Llvm will be converted to SMT-LIB version 2 formula using our tool. Lastly, this formula will be given to MATSAT and it will be checked for satisfiability. Last semester, the converter was pretty basic and we were using a custom CFG input which is created by us. Now we are directly using the .ll file created by Llvm and we focused on serious benchmarks from SVComp. Also, we try to optimize our encoding and eliminate redundant formulas. And now I will focus on some instructions we developed this semester. So firstly, signal and wait. As you know, signal and wait are thread functions which are done by condition variables. If a condition variable is called with a wait function, that thread cannot execute for the next steps until a signal matching signal function is called. This is our encoding. We have a condition variable here, and when the wait instruction is called, that means empty5 will be true, and then this formula will be false and the trend 1 won't be selected until the matching signal function comes. Now malloc, as you know, malloc is a dynamic memory allocation instruction for C. Actually, this one's very hard to encode because there is no pointers or aliases in SMT-LIB. So we just put a boolean variable for malloc which states if the malloc operation is successful or not successful, which is non-deterministic. For string and snippet operations, we just use character ASCII numbers as character representations and made a bit vector array using these values, because there wasn't any simple code to make a string representation in SMT-LIB. We just used SMT-LIB array select and store operation. Select operation chooses and sorts arrays index and store copies that select value to target arrays selected index. That is done for each index in the source variable. The important thing to consider for implementing function calls were like following: relating the function call to a thread, because when a function is called, the thread shouldn't move in the next steps until the function is completed. Also, the parameter and return variables should be copied accordingly. And lastly, if a parameter is a pointer parameter, instead of copying it, we should use the main variable's values. Here is an example function call. Thread1 makes call enq1 true, so in the next step enq function would be called and thread1 can't be called. Also, the x variable in the enq function is initialized, all values as well. For the store operation, we did a change. The global variable was store mechanism is replaced because for the loop cases it wasn't working. Instead of creating an additional variable, now we are creating copies of global variables for each execution step. So if there is a store operation in the next step, the value will be the stored value, otherwise it will stay as the same. For scheduling, we were explicitly stating the program content of next step in every instructions for every inactive thread, and it was very inefficient. Instead, this year we are just setting it on the start of the bound, like following. If thread 1 is not selected, its program content will stay the same, otherwise it's true and it will be decided by the instruction execute. This is our table. Plus means the instructions in these benchmarks are complete, and maybe it might need some minor bug fixing. For the minus ones, it means we need to implement a couple more instructions to solve these. As the future work, we can complete software completion benchmarks, all of them. Also, we need to do more testing and more minor bug fixing for these benchmarks. After that, we can encode our optimization, and we can do research and some new features to our tools, such as shutdown memory, to make memory operations easier on SMT-LIB. Thank you for your attention.